China has just taken a major step into the future of long-range aviation. The CH-7 unmanned stealth bomber has completed its first flight, and this breakthrough signals that fully autonomous, high-end flight is no longer experimental. It's happening now. This video explores how China achieved this milestone, why it represents a turning point in advanced aircraft design, and what the emergence of a second, even larger unmanned stealth platform reveals about the next era of long-range aerospace technology. Let's dive in. The CH-7's first flight marks a defining moment in the evolution of unmanned aviation because it demonstrates that a concept once shown only in models and prototypes has now transitioned into a functional, flying platform. When footage confirming the aircraft's successful flight was released on November 12th, analysts immediately noted that this wasn't a small test drone. This was a full-scale, flying-wing stealth aircraft developed by the China Aerospace Science and Technology Corporation's 11th Research Institute. One of the most striking technical details is the CH-7's 26-meter wingspan. That measurement places it below the 33-meter wingspan of China's H-6 bomber, yet the CH-7's internal layout gives it a clear efficiency advantage. Without a cockpit, pressurization systems, or life support hardware, engineers had more room to allocate volume to fuel storage, avionics, and precision-guided payload base. This redesign reflects a fundamental shift in how long-range aircraft can be structured when there is no pilot on board, allowing the CH-7 to reach distances previously achievable only by larger, crewed aircraft. The flying wing design is equally important. This shape is used primarily to reduce radar reflectivity by eliminating hard angles and protrusions. It's a smooth, blended structure that redirects radar waves rather than bouncing them back to detection systems. The fact that the CH-7 successfully flew with this design confirms that its control algorithms, aerodynamic modeling, and stability systems have reached a dependable threshold. Flying wing aircraft are notoriously difficult to control, especially during takeoff and landing, because they lack tail surfaces that provide natural stabilization. The CH-7 passing this test validates China's growing expertise in autonomous flight control systems. Another indicator of the program's maturity is the timing of this flight. The aircraft was revealed during November 2024 near the Zhuhai Air Show, when it was already seen undergoing runway trials. For a large unmanned aircraft in this class, moving from runway tests to an actual flight within about a year is unusually fast. This suggests a high degree of confidence in pre-flight evaluations and computer simulations that were conducted before the aircraft ever left the ground. What elevates this achievement further is the CH-7's intended operational role. It is designed for high-altitude, long-endurance flights where it can deploy precision-guided equipment from internal bays while maintaining a low profile. This type of capability relies heavily on advanced composites, low observable coatings, and thermal signature management techniques, areas where China has rapidly advanced during its development of fifth-generation fighters. The arrival of the CH-7 in the sky makes one thing clear. Unmanned, stealth-optimized aircraft are no longer distant concepts. They are now entering real testing phases, collecting aerodynamic data, and moving toward operational readiness. And the CH-7 is only one part of a much larger transformation. While the aviation world was still reacting to the CH-7's progress, a second breakthrough emerged, this time involving a much larger unmanned stealth aircraft. This new platform, whose official designation has not yet been published, gained attention when satellite images taken in June showed a massive flying wing aircraft stationed on a secured runway. The most compelling detail was its wingspan, visibly wider than the U.S. Air Force's B-21 Raider, which is itself one of the most advanced stealth aircraft ever developed. Such an expansive wingspan implies a completely different mission profile from the CH-7. Longer wings allow for greater lift efficiency, which is a critical factor for intercontinental range missions. A larger wingspan typically means more room for fuel storage, electrical systems, and high-end sensor arrays. When analysts saw that this aircraft had completed its first flight by October, it became clear that the program had matured significantly before the public ever knew it existed. The most striking aspect of this discovery is how it reflects China's rapid expansion in high-end aerospace research. Developing a large, unmanned flying wing aircraft requires breakthroughs in structural composites, distributed sensors, and autonomous control. The smooth surface geometry visible in the satellite images suggests advanced manufacturing techniques similar to those used in China's fifth-generation fighters. Material technologies such as radar-absorbent composites and thermal control surfaces, developed originally for aircraft like the J-20 and J-35, appear to have been adapted for this much larger platform. This larger aircraft represents a shift in long-range aviation philosophy. Traditionally, strategic-range aircraft required crews capable of staying alert for long missions, consuming resources, and imposing limits on duration. An unmanned platform eliminates nearly all of those constraints. It can remain airborne for significantly longer periods, follow more efficient flight paths, and perform long-distance operations without needing pilot rest cycles or support for onboard life systems. The existence of this aircraft also highlights a growing confidence in automation. Flying wing aircraft, especially at this scale, require constant fine-tuning of their control surfaces to maintain stability. To allow an aircraft wider than the B-21 to take off, fly, and land autonomously indicates the development of robust onboard processors, reliable sensor fusion, and complex algorithms that can predict and correct aerodynamic behavior in real time. What sets this development apart from the CH-7 is its likely purpose. Where the CH-7 focuses on long-range precision and high-altitude efficiency, this larger unmanned aircraft appears tailored for extended intercontinental flights, persistent observation, or other roles requiring exceptional endurance. Instead of functioning as a tactical platform, it rises to the level of a strategic asset, one capable of long-distance coverage without the physical limits associated with a crew. Together, these two unmanned aircraft reveal a layered approach. The CH-7 fills the long-range tactical role, while the larger platform extends reach into global aviation territory. This two-tier structure is unlike anything else currently demonstrated in the unmanned world. The significance of these developments reaches far beyond the aircraft themselves. They illustrate a fundamental shift in how advanced aviation will operate in the future. The most important detail is that autonomous flying wing platforms can now perform missions traditionally restricted by human endurance, cockpit design constraints, and the physical limits of aircrews. By removing the need for onboard personnel, designers gain freedom in shaping the aircraft for efficiency, altitude, and persistence. One critical insight comes from understanding the CH-7's intended functionality. With its internal storage for precision-guided systems and its aerodynamic design optimized for high-altitude flight, it can remain in the air far longer than traditional platforms. Endurance transforms capability. If you enjoyed this video, don't forget to like, share, and subscribe. Thank you for watching. See you there.